This is the last section that we are going to cover in Unit 10 or Chapter 9. I probably took this from your book. I actually don't remember exactly where it came from, but probably your book. This is a statement that might be a little bit hard to understand. The speed of radioactive isotope decay is predictable, and the emphasis is on the word predictable. So what does that sentence mean? It's a little bit vague. What does it mean in English? The way to understand what this sentence means is to conduct the following thought experiment. Imagine that I have 16 carbon-14 atoms, and here they are. There are 16 carbon-14 atoms, and if you remember from earlier in this unit, we said that carbon-14 atoms are unstable. If you wait around long enough, a carbon-14 atom will decay into nitrogen-14. So the first question is, how long does it take to convert half of my 16 carbon-14 atoms into nitrogen? And so let's just pretend. It doesn't take an hour, but let's just pretend that it does take an hour. If we start out with 16 carbon-14 atoms, and let's say that it takes 1 hour to convert half of them into nitrogen-14. So here are 8 out of the 16 converted into nitrogen-14. The question, or the thought exercise, and you can pause and think about this. Some of you may know the answer already, some of you may have reasonable guesses, but the question is this. Now that we have only 8 carbon-14 atoms left, how long does it take for half of the remaining 8 to be converted into nitrogen-14? In other words, if it took an hour to have 8 of these 16 converted into nitrogen-14, how long does it take to get 4 of the remaining 8 to be converted into nitrogen-14? You can pause and think about that. The answer, which may or may not be surprising, is that it takes an hour as well. So it took an hour to have 8 of the 16 converted into nitrogen-14. It takes another hour to have 4 of the remaining 8 converted into nitrogen-14 as well. And some of you may know that, some of you may have even guessed that, but it's not immediately obvious that that would be true, that it would take the same amount of time. But it is true. It takes a certain amount of time for half of the radioactive isotopes to decay. And it doesn't matter how many halves you have already decayed. In other words, it takes the same amount of time to decay half of the remaining carbon-14, no matter how many halves have previously decayed. And there's a special term for this, which you may have heard, and I mentioned this on a previous in a previous slide in a previous section. The time to decay half of the radioactive material is called the half-life of that radioactive isotope. So it turns out that carbon-14 does not take an hour for half of it to decay. It takes much longer than that. But the amount of time that it actually takes for half of the carbon-14 to decay into nitrogen-14 is called the half-life. It's kind of covered up here. It's called the half-life of carbon-14. And there is a half-life for every radioactive isotope that has been studied. So one of the punchlines is that different isotopes have different half-lives. For carbon-14, the half-life is actually 5,730 years. So if you started out with a bunch of carbon-14 atoms and you waited 5,730 years, approximately half of those carbon-14 atoms would have decayed into nitrogen-14 at the end of 5,730 years. And then if you waited another 5,730 years, the remaining, what was left over of the carbon-14, half of that again would be converted into nitrogen-14. And this number, 5,730 years, is specific to carbon-14. That's how long it takes for half of the carbon-14s to decay on average. But that's not true for other isotopes. As an example, P32, or radioactive, this is a radioactive form of phosphorus, it has a half-life of about 14 days, so about 2 weeks. So if you start out with a bunch of P32 atoms and you wait 2 weeks, half of them will have decayed into something else. If you wait another 2 weeks, half of the remaining half will have decayed. In comparison to carbon-14 and P32, uranium-235, which I mentioned as being an isotope that could be used to generate electricity, uranium-235 has a half-life of 704 million years. So it's an incredibly long amount of time before half of the uranium-235 atoms, if you had a chunk of them, would decay into something else. I very often present this slide, and students will stop me at this point, especially after I've pointed out the half-life of uranium-235 as being 704 million years. And very often the students ask, how is it possible to know this answer if you have to wait around 704 million years for half of the stuff to be gone? And if you're thinking that that's a perfectly reasonable question to ask, it turns out that you don't have to wait for half of the material to be gone. You can wait for much less than half of it to be gone, and there are equations that can be used that have been developed over the years to actually figure out what the half-life is, even though only a tiny fraction, much less than half of the isotope, has already decayed. And the same is true here, right? People do not live 5,730 years, so there are estimates that are made using a lot of fancy math to figure out what the actual half-life is for things like carbon-14 and uranium-235. P-32 is a little bit different. Its half-life is only 2 weeks, so this radioactive isotope of phosphorus is actually used in biological laboratories a lot of the time. And if you get a shipment of P-32, usually it is blazing hot, which is the colloquial term for extremely radioactive when you get it from the FedEx delivery guy, but after about a month, which is about 2 half-lives, most of the radioactivity is gone. But these other isotopes, you actually need a little bit fancier math to figure out their half-lives. There are a number of mathematical questions that can be done using the ideas behind half-life. I will go over a couple of them with you here, and then we will talk about medicines in a few minutes. So here's an example half-life question. If you start with 10 grams of P32 and the half-life of P32 is 14 days, how much P32 is left after 42 days? So the way to deal with this question, the way that I typically deal with this question, is to make a table of the information. So how much do we start with? We start with 10 grams. So I make a table that usually has 2 columns. The amount of radioactive material we have and the amount of time that has passed. So at the very beginning, when no time has passed, I'm calling that 0 days, we have 10 grams of radioactive phosphorus, of P32. And then I basically ask how much is left over after a certain number of days that relates to the half-life. So if we start with 10 grams at the very beginning, at day 0, how much is left after 14 days? Well, half-life means that half of the material half of the radioactive material has decayed. So what's half of 10? Half of 10 grams is 5 grams. So after 14 days, we should have 5 grams of P32. The next question is, how much is left after another 14 days? And in another 14 days, it's going to be 28 days. So how much is left after another 14 days? Well, it's going to be half of 5 grams. And half of 5 grams is 2.5 grams. So after 28 days, we should have 2.5 grams of P32 left over. And then you can ask the question again, how much P32 is left after another 14 days? Another 14 days is actually 42 days, which is what the question was asking. How much do we have after 42 days? Well, it's going to be half of 2.5 grams, and half of 2.5 grams is 1.25 grams. So after 42 days, we're going to have about 1.25 grams of P32 left over out of the original 10 grams that we began with. So at day 0, we have 10 grams of P32. After 1 half-life, after 14 days, we have 5 grams. After 2 half-lives, we have 2.5 grams. We have half of the 5 that was left over. And after another 14 days, which is 42 days, we have half of 2.5 grams, which turns out to be 1.25 grams. And so this is the standard way that you should do these types of half-life questions. You make a table, you list the amount of radioactive isotope that you start with, you mark that as day 0 or time 0, and then you ask how much is that left after 1 half-life, how much is left after 2 half-lives, etc., until you reach the time that you're interested in. Here is a slightly different question, but the approach to dealing with these questions is almost always the same. Here it says you have 4 grams of carbon-14, and the half-life of carbon-14 is 5,730 years. How long will it take to create 3 grams of nitrogen-14, presumably from these 4 grams of carbon-14? So how long is it going to take to make 3 grams of nitrogen-14? Well, to answer this question, again, I would make a table listing the amount of carbon-14 that I have, listing the amount of nitrogen-14 that I have, and listing the amount of time that has passed. So here's my table. The amount of carbon-14 that I have in this column, the amount of nitrogen-14 that I have in the second column, and the amount of time that's passed, in years in this case, because the half-life is in years. So at the very beginning, at year 0, we are assuming that we have 4 grams of carbon-14. And we have 0 grams of nitrogen-14 that has been made from these 4 grams. So it's all carbon-14 at year 0. And then I basically ask the question, how much carbon-14 do I have after 5,730 years, after 1 half-life? Well, I'm going to have half of what I started with, and half of 4 is 2. So after 5,730 years, I'm going to have 2 grams of carbon-14, and the 2 grams that decayed, I'll have 2 grams of carbon-14 left over. The 2 grams that decayed will have turned into nitrogen-14. So I will have gone from 0 grams of nitrogen-14 to 2 grams of nitrogen-14. So just to summarize, after 5,730 years, I'm going to have 2 grams of carbon-14, 2 grams of nitrogen-14. Then I ask the same question again. How much carbon-14 am I going to have after another 5,730 years? Well, it's going to be half of 2 grams, which is 1 gram, which means 1 gram is going to be converted into nitrogen-14. And we already had 2 grams that were previously converted, so 2 grams previously converted plus another gram of carbon-14 converted into nitrogen-14 is going to make 3 grams of nitrogen-14 made and 1 gram of carbon-14 left over. And 2 sets of half-lives, or 2 sets of 5,730 years, is 11,460 years. And that is basically the question. How long will it take to make 3 grams of nitrogen-14? Well, here's our 3 grams of nitrogen-14. It's going to take about 11,460 years to get there, if we started out with 4 grams of carbon-14. So that is how you do these types of problems. I should point out that the way that we're doing these problems only works if the problems ask for multiples of the half-life. In other words, if I asked you for how much carbon-14 you're going to have left over at some point in between 0 years and 5,730 years, that type of calculation can be done. There are formulas to do it, but we're not covering them in this course. So the only types of questions that I will ask you are the types of questions that work out cleanly, where the amount of time that passes is always going to be a multiple of the half-life.